Hello and welcome to Computational Multiphysics. Today we're going to be combining a lot of the cool stuff that we've talked about into one mega problem. We've got a voltage setup across a metal that's surrounding a piezoelectric material. And we're going to look for the voltage that gets created as a result of this, like the voltage distribution and the electric field that shows up in both the metal to cause conduction and the piezoelectric. And we're going to look at the strains that show up from piezoelectric effect and from thermal expansion from Joule heating in this metal. All right, so the first thing to do is to build this thing up in stages. We're going to be having only one variable, which is the voltage, and let's get rid of some comments that we don't need. This is going to be multiphysics mega problem. Yeah, okay, so the setup in definitions, we're going to say that the E field is equal to negative grad of the voltage. Let's give pretty descriptive names because we're going to need V later to be the displacement in the y direction, and E perhaps to be the elasticity. So we better call these things E field and voltage to give us more space with variables later. Now what we're going to do is we're going to incorporate some parameters. Let's just say that the thickness of the top layer is equal to 1e minus 3, and we'll say, let's go with 1.5e minus 3, and then the bottom layer thickness is equal to 1e minus 3. Let's say that the mid thickness is 3e minus 3, and the length in x is 12e minus 3. We'll make it a bit longer, and then we'll say that the little bit of length at the end there is 1e minus 3. We'll put in a maximum voltage of 3 volts for now, and we'll say that the thing has a conductivity of rho E is 80, resistivity rho E is 80 E minus 9, so 80 nano ohm meters. Then we will we'll use this. This is going to be enough for us to model just the metal. So next what we're going to have to do is draw out the boundary in a way that makes more sense for what we've got here. The differential equation will say that the div of J, div of current density in steady state, is going to be equal to 0. So we'll need to define what that is as well. We'll say, let's put this below the material parameters. J is equal to sigma times E field. E field, yeah. And we'll need to, actually we might need a different sigma later. So let's call it sigma E is 1 over the resistivity. So conductivity 1 over resistivity. All right, then contour. So suppose we change nothing, we should be able to get this to work. Okay, all good. Contour voltage painted. Yeah, so it's just 0 everywhere because we haven't set any of the different boundary conditions. And now we can draw this region out. So we want to draw just this shape. Let's start at the, how about starting at the bottom left and working our way up and then around and back. Okay, so we'll start at 0, 0, and then we'll take line 2, LX 0 to LX HB plus HM plus HT would be the total height, to 0 HB plus HM plus HT, and then we're going to go and modify the boundary conditions. Value voltage is equal to V max. Line 2, same position, up at the top left, 0, and then down by HT. So just HB plus HM. Now we'll reset the default boundary condition because we don't want a value of voltage being stuck on this part. So we'll go back to load voltage. Again, we didn't have to specify that load voltage is 0 at the start because that's there by default. So with load voltage equals 0 now, we can walk this interior part of the boundary. So we'll say line to Lx minus Lt would be this x coordinate, HB plus HM, to the same x position, but just HB up, and then to an x position of 0, and the same height. Now we'll again set a value condition for voltage. Value voltage is 0. Line to close. Okay, so let's see. Aha, looks good. We've got a voltage set up around the top. And we have something that looks like it resembles what the geometry would be if we had the slightly higher thickness up at the top and this limit over here on the right. Okay. We can also plot what the current is. So let's do a vector plot. Vector of J. How about normalized? Yeah, all right, so there we go. So the current is moving around there. It looks like it gets a little bit spiky right at the corners where things are a bit hard for the finite element method to resolve. There's not quite enough detail there probably. You would expect the current to spike up a little bit where it can cut this corner. It's a shorter path if it can go there than if it has to go all the way around. Imagine if there's a bunch of people just trying to get from there to there as fast as possible, or a bunch of cars, then this is a shorter path, so maybe they can try to zoom across there rather than going to the outer spot and then making their way around. Okay, so we can maybe improve things a little bit. The mesh is not looking so dense there. Maybe we can improve things by specifying error limit is 1 e minus 6, so give a relative error that's lower. And yes, indeed, the simulation decided, you know what, we don't really need a lot of density over here. There doesn't seem to be a lot happening. But right around here, ooh, that's kind of interesting. There's some curving going on. We need a lot of extra mesh density built in. So that has smoothed things out here. I mean, the vector plot still might look kind of maybe spiky because it's got a uniformly spaced set of vectors. So this doesn't actually correspond, the density of the arrows here doesn't correspond to the actual grid density that's being simulated. You can see in some places over here it's got a lot denser arrows than is actually being simulated, whereas over here it seems like the arrows are less dense than what's actually being simulated. Next step is to add in the dielectric. So we're going to make a new region. Maybe we'll call this region metal, and then we'll make another one, region dielectric, or maybe eventually it's going to be a piezoelectric, but sure, dielectric's okay for now. And this is going to start at the bottom corner here, and then go across and up and back down. So start at 0 HB, line 2, 0 Lx minus Lt HB to Lx minus Lt HB plus HM to 0 HB plus HM to close. All right, so this in the mesh has drawn this extra segment there, this interior part, but in the simulation you don't see it, and that's because we didn't specify anything different going on there. There's just a different boundary condition on this edge than here, but it's all the same material parameter, so Flex just kind of incorporates that into the same region there. The magnitude of the current that's going from one to the other is probably higher, but is the current density higher? Hard to say. Let's kind of comment that out. Can we jump back to the results? Yeah, so we're at 2.65 E10, and now without that part, it goes to 3.18 E9. So yeah, even the current density has a maximum that's a fair bit higher when we add that extra conduction path through the center. But that's not quite what we want to do. We don't want this dielectric to be a conductor through the center. So what we can do is mess with the material parameters here. We can't actually turn the conductivity completely off because this gives an empty equation in region 2. What that's talking about is this differential equation here, div of j equals 0. Because we said that j is sigma e, if sigma is fully 0, then this equation just says 0, div of 0 equals 0. And that doesn't give you any information to be able to solve for what's going on with the voltage. So that's no good. We need to do something about that, and we can fix it by, instead of saying that sigma is 0, we're going to make sigma so low that it's practically 0. 1 is a good example of that, because with the resistivity of around 100 e minus 9 or 1 e minus 7, that means the conductivity is more like 1 times 10 to the 7 or 10 million. So a conductivity of 1 compared to 10 million is basically 0, and this is going to allow us to solve the simulation again. So you'll notice that the answer is almost the same as it was when we didn't even have the dielectric there. 2.97 is the max. It's actually a little bit lower than it was without that, and the voltage gradient looks almost identical, right? The voltage across this thing basically still starting at 3, ending at 0, and having the same spacing as it did when we didn't have that dielectric there. Now, that's not really the full story of how this dielectric should be behaving, because although it can't conduct very well, it can set up a polarization field, and this changes things according to this D field. So we previously were saying that the divergence of the D field is the free charge, and it's kind of tempting to set up, oh, well, let's just suppose the free charge is 0, so that means div of j is 0 and div of d is 0. So maybe we can say div of j plus d field is 0, where d field is equal to epsilon, epsilon, maybe like S, in reference to what we're going to be doing for piezoelectrics later, epsilon S times E field, and epsilon S we'll say is epsilon rel times epsilon 0, where epsilon 0 is equal to 8.854 E minus 12, and epsilon rel is equal to 0 in the metal, but is not 0 in the dielectric. It could be quite high in the dielectric. So yeah, this lets us solve things just as well. It doesn't look any different from a current density perspective or even from a voltage gradient perspective. It seems legit, seems like nothing's being changed from this, because 1,000 is not very large compared to this 10 million that we had for the conductivity in that metal, but perhaps it makes a difference if the conductivity is turned down a fair bit. So imagine if this is E minus 3. Now we've got a fair amount of stuff going through. So the J is still 0, or more or less closer to 0 in this area, but the field is now being modified by this dielectric's presence. But this is a little bit of a funky way to solve things, because it doesn't account for the actual, it doesn't account for the fact that these two things have different units. So a better way to deal with this, rather than directly adding J and D field, is to make up a separate differential equation. Div of D field is equal to the free charge density. And what we can do is, now we've got, well, this isn't going to be able to solve for stuff. If we say the free charge density is 0, the problem is we've got too many equations. So we need to make another variable. And we can do that. We'll make the free charge density a separate variable. Now we specify which one's associated with which. So we'll say that this one solves for the voltage, and this equation solves for rho free. And we can go through and solve this setup again. Now it actually looks very similar to what we were getting before, with no boundary conditions on the free charge density. That's not so surprising. Let's get some extra contours going in here. So how about a contour of row free painted and see what's going on with that. It looks as though we've got a buildup of positive charge at the top surface and a buildup of negative charge at the bottom surface. To change around things a little bit more, we can specify that the conductivity in the dielectric is even smaller. So that just makes sure that there's no, well, basically no current going through this part. And we get a voltage distribution when the conductivity of the dielectric is 0 that is basically the same as what was happening before we were even doing this. But the permittivity does affect how much free charge density is going to be building up on this surface. If we have a relative permittivity that's just 1 instead of 1,000, then watch what happens to the free charge density. Instead of 0.1 on the top surface, it goes down to 0.1 e minus 3, so it drops by 1,000 as well. So while the dielectric's presence doesn't change the voltage distribution that shows up on the outside, it does change from its ability to polarize how much charge is going to build up on the top surface and the bottom surface of this thing acting like a capacitor. Now we're in a position to explore what's going on with this charge and find out how the charge on the top compares to the charge on the bottom, and how it compares to what you would find for a capacitor, like a pure capacitor that's just got like one, that isn't flowing around the side of it, that doesn't have electricity flowing around the side like this thing. This is almost like a capacitor with a leak, perhaps. So to do that, we're going to want to take the integral of the charge density over this top area and the integral of the charge density over this bottom area and compare them. Unfortunately, the way that we drew the geometry makes that not possible. So the first step is going to be to change around this geometry into two different regions. We're going to call it metal top and metal bottom, and we're going to modify the drawing to just split this into a separate thing. So metal top, we're going to draw just this top half. Maybe we're going to start here, go down about halfway, over, up, and then to close. And metal bottom, we're going to do the same thing, but inverted, and there to close. Okay, so let's give that a shot. So we're going to go start at 0 HB plus HM, line to Lx minus LT. So that's from there over to the right. Then we're going to go down to there. HB plus HM to Lx minus LT. Now we want to go halfway down, HB plus HM over 2, and then over to the right. Lx HB plus HM over 2 to Lx HB plus HM plus HT to 0 HB plus HM plus HT. Put this on a different line. Then we'll specify the boundary condition. Value of voltage is Vmax. Line to close. So if this is correct, then what I've just drawn is this top area and then to a close right there. So let's just check that out by commenting everything else out. And then I think for this to work, we're going to have to set epsilon rel is non-zero. Otherwise, we're going to get a differential equation empty thing there. But let's check. Oh, no, it still works. So by setting it to row free rather than 0, it's able to still solve it. Okay, so that looks good. It's a fixed voltage of 3. This actually has gone and drawn just that top part right there. And then the other check is that this hasn't actually changed anything in the, oh, right. Sorry, this is an interesting feature of Flex. If you draw something and then you draw it again, then what you end up doing is canceling the original thing that you drew. So we've overwritten it and eliminated that first region. All right, so let's fix that. So we'll eliminate this, the rest of this drawing, and we'll add in a new region. region metal bot, and we'll start at the opposite of this. So this is going to be very similar to the previous drawing, except that we're going to go here and then up and then down. So we'll start at just H bottom, line to the end, still H bottom, and then up to the same midpoint, out to the same midpoint, and then here, down to 0 height, and then to 0, 0, and this time we'll say value voltage is 0, line to close. So this should now be doing exactly the same simulation as before. Yes, all good. Okay, now we'll do the same thing for this middle region. Let's call it piezo bottom, and we'll start there, except now we'll only go up to HM over 2. And then we'll make a very similar region, piezo top. And this one will start at HM plus H bottom in height, there, back, and close. Okay, so from a mesh perspective, what we did is we drew this top part as one region, and then metal bottom goes like this, and then we did piezo bottom, which does this one, and piezo top is there. Okay, so that is the updated geometry drawing and gets the entire thing all done. We've got the voltage, we've got the current density, and the charge density. Next up is to calculate what the total charge is on the top plate and the bottom plate. And we can do this with integrals. So let's add in a summary section, and we'll say Q top. Oh, maybe we'll make a variable for this. Q top would be equal to the integral of the free charge density over metal top plus the integral of the free charge density over piezo top. Then we'll make a similar one for the bottom. Rho free over metal bot and over piezo bot. And then we just need to report them. All right, and this is promising. We've got exactly the same charge on the top plate as the bottom plate, except that the top plate is positive that value while the bottom plate is negative that value. Just what you'd expect for voltage across for the charge on each side of a capacitor. Even though this isn't quite a capacitor, we still got the same result for that voltage. Next thing we could do is we could use some vector calculus to compare with what's going on with the D field. If this was a pure capacitor, then what we'd expect is that the electric displacement field is entirely isolated, entirely contained in just this middle region here. Let's actually check that. We can make a vector plot of D field normalized and see where the D field exists. Yeah, so by setting the permittivity to actually just 0 in this metal region, the D field only exists inside the dielectric. Now, the D field divergence is supposed to be equal to the charge density. So that means that we should be able to say that the total charge, maybe on the top plate, would be equal to the integral of the charge density over the top plate with respect to volume. And this is equal to the integral of the divergence of D over that same top plate. And that is by the divergence theorem equal to the outward flux of D over the boundary of that top plate. And since D only actually exists between the capacitor plates, we don't have to go around all of this. We just have to go across the midpoint here, right? Or across any point between this, along any line in between. So that means that we can say that this is the same as the integral of d dot dA over, let's say, the midplane. And since the midplane's normal, this is like some plane across the center of this, the midplane's normal vector is just pointing in the downward direction, then this is going to be equal to the area of the midplane times, well, not times, it's really like the, so we can get rid of the dot product here by saying negative d field, maybe d field z, times the area, no longer a vector integral. Okay, so that's what we're going to be thinking about to find this charge. What that means is we can do qtop check, qtop by d field is the surface integral of z component, oh, not z component, y component of d field. That's the part going up, except we're actually going to need negative of that over midline. And what we're going to do is make a feature called midline, which just goes across the middle of this. Start at 0 and HB plus HM over 2. Line 2, LX and HB plus HM over 2. So this goes all the way across the center of this, and we'll see if we can calculate a check of what the charge should be using this method. Oh, yeah, needs to be in quotes. Okay, pretty good. So qtop evaluated by just directly volume integrating the charge density gives us this. qtop by doing the integral of the z component of the d field over the center line, which then turns into a plane when you multiply it by a depth of 1, gives us this value. So we end up with exactly the same, or at least mostly the same result, whether we do this check or the actual direct calculation of the charge. Another thing that we can do is compare this with what the charge should be for a parallel plate capacitor. And that would be the voltage times the capacitance. And the capacitance is epsilon r, or really like epsilon, which I guess we're calling epsilon s. Yeah, to avoid confusing it with strain later. Epsilon times the area, which is the length times the depth in and out of the page, and that's just 1 for this two-dimensional simulation, over the thickness, which is hm. So this is epsilon A over D. That's our capacitance for a parallel plate capacitor, multiplied by the voltage across it, should give us the charge on that capacitor. Now this one, we're going to evaluate it in the middle of the capacitor to just make sure that we're using the right permittivity. So this is going to be value of Q theory. We'll give an x value of Lx over 2 and a y value of HB plus HM over 2. All right, so the theoretical one for a parallel plate capacitor is a lot higher, but that's because the voltage on this is not actually just the fixed voltage difference over the top and bottom surface. The voltage is on average a lot lower because it's decreasing from left to right. Yeah, so this is the charge that would happen if we had this 3 volt thing there and this 0 volt thing there all the way across. So not surprising, the actual charge that shows up is somewhat lower than this one. That's kind of a check already, but we can do an even better check by going and changing LT to 0 to make this into an actual capacitor. So now the voltage is just fixed on the top surface, fixed on the bottom surface at 0. We've got this scaling voltage throughout the middle. There's no current density anymore. And all of the D field is uniform. And in this situation, we end up with the same charge on the top as we had on the bottom, and it agrees with what we calculated with theory. Okay, the next thing to do is to incorporate a piezoelectric effect by making this center piece, this dielectric, not just a dielectric, but also a piezoelectric. All right, so we can do that by referring to a previous simulation file. This is one that was doing a, this is one from a previous assignment, I think from the piezo assignment this year. Yeah, so here we've got this piezoelectric kind of bending thing going on. What we'll do is we'll keep it in 2 dimensions. So we'll just have a variable for u and v for the displacement in x and in y. Then we'll add in this global max magnification thing, again converting it to 2 dimensions so that we'll be able to have a good displacement plot later. Maybe we'll put in that displacement plot now. So this is the grid plot stuff that we're going to need in the plot section, just so we don't forget to do that. Yeah, okay, that's good. Next, what we'll need is specifications for, okay, we don't need this. We are going to need to set up what E field X, Y, and Z are, and this is going to be done in terms of components. So right after we've defined E field, we can set up E field X is equal to X comp of E field Y is equal to Y comp of E field. Now we could say E field Z is equal to 0. That's probably going to be good. Then we'll be able to save some time with copying and pasting stuff. We will need a set of stiffness matrix components. Let's see, where do we put that in? Sure, why not right here? Then thermal expansion stuff, which fine for now can be 0. And then some piezoelectric coupling coefficients. Strain, mechanical strain, Hooke's law, that looks all good. Now, to make this into a 2-dimensional thing, we are going to need some stuff to work out a little bit differently. So first we'll just have u and v differential equations, and we can't have any z derivatives in there. So we'll get rid of those. Up here, we could go and eliminate all the things depending on z, but rather than doing that, we can just set the z strains as fixed to 0. These things that involve these z derivatives, nothing can change in z, so we'll set those equal to 0, and that should make them, along with E field Z being 0, have no effect on the deformations. Okay, so the other thing we'll need, I suppose, is the delta T, or delta temp, right? Delta temp, yeah. Delta temp is equal to 0 for now, and some boundary conditions to hold it still on these edges. Value u is 0, value v is 0. Let's put that on both of the electrical contacts just to see what's going on. Okay, I'm not sure if we got everything there. We can give it a shot. All right, it did something. Fixed on this surface, fixed on that surface. From the displacement that we've got set up in here, we've ended up with an interesting kind of bending down effect. This primarily seems like it is to do with, let's see, it looks like it's mostly an XY shear that's happening, but it's non-uniform, so it changes as we move from one piece to the next. What if we get rid of LT? This looks like a much more pronounced shear strain in this. This is a negative XY shear strain because per positive step in X, we've got a negative displacement in Y. So that would be if whatever electric field we have here, which in our setup is almost entirely an electric field in the negative Y direction, then we would be having a displacement, we'd be getting an XY shear strain, which is negative from a negative electric field in the y direction. So let's check. The component of D that translates y electric field to XY shear strains is D26. You can see that from this multiplication right there, XY shear strain, and D26 is the one that does it. And that component is positive, so that makes sense why the negative field would be giving us a negative strain. Now, we can explore this by, say, setting D26 equal to 0. And when you run this, it looks like not much has changed. It still has this shear component, but the actual displacement is quite a lot lower. So we can get a feeling for this by, say, reporting on this plot. Report val of, let's say, V at Lx HB plus HM over 2. So now we've got a displacement of 2.6 e minus 12 at that spot, whereas when we were not commenting out D26, the displacement is quite a lot larger, so 20 times larger or so, negative 4 e minus 11 instead of 2 e minus 12. So this has quite a big effect turning it off. It just isn't visible because we're scaling the thing by the absolute displacement, by the biggest displacement. Okay, so if we instead add in some other displacements here, maybe negative 2.3 e minus 12 in y from y, and 2.3 e minus 12 in x from y, now we get a little bit of a bulbing there, and it's going to be more obvious what happens when we turn this thing off. So it doesn't bend down nearly as much. Still does, but not quite as much. And we've got this deformation showing up axially now as a result of the electric field that we're applying. Now, one thing that's not quite right about this setup now is the charge calculations. So with a piezoelectric material in the center, then we have not just this inverse piezoelectric effect, that is where electricity creates stresses and strains in the material, but we have a forward piezoelectric effect where stresses and strains create charge displacement in the material. So to deal with that, we're going to need to technically modify what we were doing to find the D field from just permittivity times E field to something that includes either the D matrix multiplied by sigma and then epsilon T times E, or the E matrix times epsilon plus epsilon S times E. To get this thing to work, we can well, first we need to figure out what epsilon T is for a given material, and then we need to work out what just a modified equation here. So let's suppose in this setup that the epsilon that we were given was already epsilon T. That'll make it a little bit easier. So suppose we've got the T component here, then we can just take D and multiply it by that sigma. So yeah, let's see. Rather than epsilon S, epsilon rel, that sort of thing, let's imagine that it was just epsilon T that we're starting with, and then we'll say epsilon T times E field, except rather than just that, we'll need to add in D field piezo, and let's say D field piezo is the vector addition of its X component, Y component, and Z component. Here's what I've got in mind. I'm going to manually write out this matrix multiplication of D times sigma in each of these components. So D field piezo X will be D11 times the first component of sigma, and we can just look at this in this row to remember what order they're in. D12 times SY, D13 times SZ, D14 SYZ, D15 SXZ, and D16 times SXY. Now a lot of these are actually going to be 0 in 2 dimensions, but that's okay. This is going to allow us to extend it into 3 dimensions in case we ever needed to do that. Now we'll just take the the thing that we copied and modify the components to actually carry out this matrix multiplication. Okay, so this should have done something. Oh, not epsilon s, we're going to change it to epsilon t now. And I think that does it. Okay, great. Did it change the D field? Yes, it looks like we now have some small D field showing up in this material, in the metal there, because we didn't actually turn off the piezoelectricity in the metal. That's another thing that we should probably get on. So let's take this set of matrices here, and we'll go into the metal and make sure that it has no piezoelectric effect. So we'll just set all of these equal to 0 inside the metal. And another thing we probably should do is make the metal have a different stiffness matrix, so that it is actually the stiffness matrix associated with an isotropic material like a metal. Then we can incorporate just the electric field or just the stiffness that we need for the metal in order to give all of those, to give the correct calculations. Okay, so here we go. Metal top, metal bottom there, and now we again don't have any D field showing up in the metal, so that's good. The charge is very similar. Did it make any difference to what we were calculating without that forward piezoelectric effect? It doesn't seem like it. They both still agree quite well. In this setup, the stress is quite low because of the boundary conditions. So we don't actually have a very high amount of difference to the charge that we were getting earlier. So for this to be coupling back, we need that the D field is modified by the piezoelectric effect. And if there's no stress in the material, then this isn't actually modified from what we were saying before in epsilon t times E field. So we could try setting up different mechanical boundary conditions. Like suppose on the top and the bottom of the metal, we say the outside of this cannot move. I put those in the wrong spot. We need to put them here after the start. Now, the only thing that can move is that part there, but generally things are pretty fixed. And aha, now things have been modified. Still not a huge amount. It's like looks like about a, like a 5% difference from what we had before? 5-10% difference. So this is the effect for this particular case. This size of piezoelectric matrix, we do indeed see a change to the charge, whether we're holding it still on the edges or not, and that's kind of neat. All right, so let's turn off these value conditions, holding the thing still around the metal, get it to move again. And the next thing that we're gonna do, we've got a couple of things left to do. We want to change the stiffness for the metal to be an isotropic materials matrix. We want to perhaps consider what it would be like if we actually incorporated quartz rotated in the appropriate direction rather than just making up our own piezoelectric coefficients. But first, what I'd like to do is incorporate heat flow and thermal expansion. So for this, we're going to need another variable. This is the last variable we can fit in, and we're going to put a variable as, and we're going to make the variable temperature. So the temperature is determined by thermal boundary conditions and a conductivity K. I don't think we're using K yet, so we have this as a parameter. Let's just say K is 100, and we'll imagine that the temperature all around the edges of this thing, perhaps on this part where the voltage is fixed. Let's just make it simple. We'll say that the value, whoops, erased some stuff. That's with the insert key. Insert toggles whether typing will erase things or insert into where you left some space. Okay. So if you ever find that you're typing over, the reason that it started doing that is probably because you accidentally hit the insert key, just in case you weren't clear on that. So value temp is equal to 20 on this top edge. And yeah, we can just leave it like that for now. So what we'll do is we'll say that Q dot, the volumetric heat flow, the heat flux density, Q dot is equal to negative K times the grad of the temperature. Then we'll say that the volumetric heat generation, after we've calculated J, yeah, anywhere down here, we can now say Q dot vol is equal to the dot product of J and E field. Then, in the differential equations, we'll go for the steady state heat equation, where this is 0, and we can move this part over to the other side and get that the divergence of heat flux density is equal to Q dot vol. Okay, so we expect that the temperature is going to stay around 20 on this edge, but be quite high in other places. And first, since we didn't say the temperature affects anything else, none of the rest of the things that we simulated actually changed. But if we make a contour plot, then we'll get to see what's going on with that temperature. Everything has exactly the same conductivity here. We didn't make it different from one spot to the next. Let's see. It looks like the temperature is just fixed to 20 everywhere, which is a little bit surprising. Oh, you know, it's not quite 20. Maybe it's close to 20, but it's not quite 20. The current is very low because we don't have a path for current. So let's give a path for current by opening up this end part. So now current can flow again. We should expect now to get a lot more heat generation. Aha, yes. So temperature is 20 there and then rises up, not much actually, from the geometry that we've got in this particular problem. So we get a higher amount of heat generation there, and not surprisingly, we've got a higher temperature in that corner than we have otherwise. So it goes down to 20 degrees around there, higher temperature over where we are generating more heat. No, actually, we probably need to change the thermal conductivity. For the metal, maybe the thermal conductivity is like 300. That's like typical of around gold. And for the piezoelectric material, really depends on what kind we're talking about. If it is quartz, then we're going to have a K, which is more like maybe 6. Not as bad as glass. The single crystal nature of the piezoelectric makes the thermal conductivity quite a lot higher than in an amorphous material. So with that setup for the conductivity, the heat capacity doesn't actually matter for steady state temperature distribution. We have a pretty different temperature gradient thing, which actually does something similar to what's going on with the voltage gradients, where you can have a high change here and less change going on in the middle. Now what's going on here? Why is this the highest temperature point? Well, because the heat is generated there, but we said it can't dissipate. So we said this part is fixed to 20 degrees, but over here we didn't do anything like that. So the temperature is able to increase all the way along towards this, this bottom left area there. The reason that this isn't quite a lot higher of a temperature for this thing is because we set the electrical resistivity of this metal at pretty high resistivity for a metal. So if it's more like a typical metal resistivity in nano-ohm meters, then we end up with a very different temperature profile at the end of this, where now the shape is pretty similar. It's proportional to the previous shape, except that the temperature is now 100,000 degrees instead of like 20 degrees. So massive amount of power going through if we change the electrical resistivity by a factor of 1,000,000 and ends up changing the temperature by quite a huge factor as well. So we can maybe experiment with somewhere around the middle of this and then see what is going on. So we've got a temperature going up to 135 degrees if we've got a resistivity of 80 micro ohm, 80 micro ohm meters instead of 80 nano ohm meters. Then that's a little bit more realistic for us to mess around with and see what's going on with the with thermal expansion. So to do that, let's build in some thermal expansion. And the way to do that is by making up a delta temp. Let's imagine the temperature default is 20 degrees. So we'll say delta temp is equal to temp minus 20. And we'll put in an alpha x and y of 10e minus 6. Sort of reasonable. Now let's see what goes on with the thermal expansion from this 100-degree temperature increase. Aha! So the beam now has a way larger displacement. You might remember before we put in this thermal expansion that the displacement, I think, was on the order of, was it 10 to the negative 10? Let's turn off the thermal expansion by saying delta temp is just equal to 0. Yeah, oh, even lower. We've got almost nothing on the order of E minus 12 as the displacement at the tip there. But with thermal expansion happening, the displacement became on the order of 10 to the negative 5. So much more displacement at the end of this thing. The reason it bends up, even though we don't have any alpha difference, is because now we've got a temperature difference. So the temperature at the bottom in this particular setup was way higher because we said the only place to dissipate the heat is at this one edge. So that means the bottom part heats up more than the top and is going to be bending up as a result. So the last thing to do is quite a challenge topic. This is more for people that are interested in it. You're not going to be responsible for rotating matrices on tests or exams in this course, but if you're interested in taking a piezoelectric and translating it to a different direction, then here's how you do it. This is on setting up quartz in a modified set of matrices so that we can use it with y pointing up and x pointing to the right by rotating the quartz crystal so that crystal X is up and crystal Y is to the right and crystal Z is into the page. This involves taking a rotation matrix that, or really transformation matrix, which you can get by thinking about what would happen to I hat, it's going to go to Y, J hat, it's going to go to X, and K hat, it's going to go to negative K. And then applying the inverse of this matrix is, what's the word, involutory matrix. It's its own inverse. Taking the inverse of this, because if that matrix tells you about the transformation that has to happen to the global coordinate system to get the local quartz coordinate system, then the inverse of that is what the local quartz coordinate system's opinion is going to be of a vector defined in the global coordinate system. Then you need the matrix for mirroring for the stress and strain components. It's not quite a transformation because it ignores the negative part of it, and this just swaps x and y. So that's this mirror matrix here, the one that swaps x and y. without taking z to negative z. Then it ends up being that you can get your new S matrix, your new compliance matrix, by right multiplying it by the mirror matrix, and you can get your new, oh, sorry, there's a mistake here. Not just right multiplying, also left multiplying by the mirror matrix. Yes, so SP is the mirror matrix dotted with compliance, dotted with the mirror matrix. This is matrix multiplication here in Maple syntax. And the new piezoelectric matrix is mirror matrix transpose of D, and then the rotation matrix. The reason this works out is derived in the assignment 7 solutions this year, if you're interested. And basically the idea is you use the local coordinate system's opinion of variables and say that the compliance matrix and D matrix have to work in that local coordinate system because that's what they were defined as for the material. And then to translate that to the global coordinate system, you figure out what the relationship is between the global coordinate system's opinion of variables and the local coordinate system. And that's these mirror matrices for the strain and stress, and this translation matrix for the electric field vector. Then to solve for the global strain, global coordinate system strain, you just end up left multiplying by the inverse of this mirror matrix, and you find that this is the relation between the variables. So the rotated compliance matrix is mirror, original compliance mirror, while the rotated or transformed D transpose is mirror D transpose and then the translation matrix. If we carry that out for quartz, using the compliance matrix for quartz, the D matrix, and the epsilon T, then we can work out what the equivalent, using Control 1 to put this into smaller font if you're interested, what the equivalent stiffness matrix is after transforming, and the D matrix is after transforming it. So from this, we can incorporate things into Flex PDE. The D matrix should have a 2.3 in the Y component, zeros up here, and a negative 2.3 in the 2,2 component. Next up, the 1,4 component should be positive 0.67 now. The 2,5 component, negative 0.67. And the 1,6 component is where this 4.6 E negative 12 goes. As far as the C matrix still 0.867 there and 0.698 there. For the X and Y swap, that's not surprising. Nothing going on differently here either in Z. Z's just moved to negative Z, so no change in terms of stiffness. But something has been changed over with the shear components. So now it's not a 1 point. Actually, I'm sort of surprised that this was like this in the first place. Was that actually the regular quartz one? Maybe there was a mistake in those in that previous setup. Yeah, I'm not sure where that came from. Quartz actually should have had this negative 17 E9 over in the 2,4 component, not in the 2,5 component. Anyway, now that we've moved to a new transformed version, it actually is supposed to be over in the 2,5 component, but it's supposed to be positive instead of negative. Now in the 1,5 is where we end up with the negative version of that. And the other thing that shows up is this 3,6 component, or rather 5, 6 component moving to 4, 6, moves one row up. Okay, so this should be the new setup for quartz rotated into the new coordinate system. All right, so let's check. Does this end up making much of a difference to what we had? So what could be different? We've got this 1.37 e minus 5, the charge maybe 7.4 e minus 8. Let's run it again. Okay, so 1.37 e minus 5 doesn't make much of a difference to the deformation because this is all thermal expansion dominated right now. And still around 7 e minus 8, but slightly different from what it was before in terms of the charge. Charge now affected by the forward piezoelectric effect having a very big impact from the thermal expansion dominated problem. Finally, for a metal, the stiffness matrix is going to be different. Now having the components of an isotropic setup. So what we're going to have is C11 being equal to this E times 1 minus nu times, let's see this, 1 minus nu over 1 plus nu and 1 minus 2 nu. Yeah. So these are both in the denominator. If you are not comfortable with that, you could put another bracket and put a multiplication inside. So that's C11. And C12 is equal to the same thing, except multiplied by nu, Poisson's ratio, instead of 1 minus nu. Now we'll also need to define what E is. This is why we couldn't use E as electric field earlier. So we'll say E is, actually, I wonder if an easier way to do this, it's probably better to define the general C's up here and specify what E is for the metal, maybe 79E9, something like that. Then fill out the rest of these components appropriately. C12 we've just defined up there. C13 is going to be the same as C12, and we'll make the shear ones all 0. And this is going to be G. This is G. This is G, where nu is maybe 0.33 and G is E over 1. Did I do that right? Yeah. Oh, no. G is E over 2 times 1 plus nu. Okay. G is E over 2 times 1 plus nu. So then C11, this is going to be based on these other components here. We'll make this C11 as well. And everything should be, unless I've made some mistake and forgotten something, everything should be filled out now as far as the stiffness matrix. So what we'll do then is take this stiffness matrix and apply this separately for the piezoelectric regions. Okay. So now we've got a different stiffness matrix for the metals than we have for the piezoelectric material in the middle. Doesn't change a lot because we made the stiffness of the metal actually around the same as the stiffness of the piezoelectric material, but it does mean slightly less charge buildup in the piezoelectric. That makes sense because the metal was slightly less stiff than the piezoelectric in this setup, I believe. So it ends up maybe not being moved quite as much as it was before. To explore this more fully, we can mess around with the stiffness of the metal. So imagine it's 79E6. Now the metal is not very stiff at all compared to the piezoelectric material. And we end up with, I believe, a fair bit lower charge. Was it before again? Yes, about 6 times higher when the metal is more stiff compared to the piezoelectric and actually able to move it around as a result of this thermal expansion. If the metal is not very stiff at all, so more like 79E3, then this charge displacement that we're seeing will go down quite a lot. So now only about 1 E minus 8, where a lot of that is more to do with the with not so much the thermal expansion itself, but more the, well, actually, I guess a lot of it's still to do with the thermal expansion, because the theoretical one is a lot lower. So if it wasn't for the piezoelectric effect and the thermal expansion showing up, we'd have a lot less of that actual displacement there. So there's a lot going on here. What we did today was a multiphysics mega problem, building in most of the things from the rest of the year. We solved for the voltage from the conductivity of this metal and the boundary conditions. We solved for the free charge density from the electric displacement field stuff. We solved for the stress and strain and the displacements that show up in the material, and we solved for the temperature difference that shows up from internal heat generation. Thanks for watching. I'll see you next time.